It's pretty amazing when you think about it. Everything that moves, and I mean everything, from a tiny apple falling from a tree to a massive planet circling a star, is actually playing by the exact same surprisingly simple set of rules. So today, that's what we're going to do. We're going to pull back the curtain and demystify the basic physics of force, work, and energy.
Okay, let's kick things off with a pretty big question, right? I mean, what is it? What's the invisible string that keeps a planet locked in its orbit? And at the same time, what's the deal with an apple just letting go of a branch and falling straight down? They seem like totally different worlds, impossibly complex. But the beautiful part, the really cool part, is that the same simple, elegant rules are behind both of them. And where do all those rules start? Well, they begin with one single, fundamental concept. It's the true mover and shaker of the entire universe: force.
So what exactly is a force anyway? When you boil it all down, it's really just a push or a pull. That's it. It's what makes stuff start moving, stop moving, or, swerve and change direction. But here's the key thing you got to remember. It's not just about how hard you push. The direction you push in is just as important. Both those things, the strength and the direction, they're absolutely essential.
Now these forces, they basically come in two main flavors. First, you've got contact forces. These are the ones that make perfect sense, right? You have to actually touch something, like when you push a box across the floor. But then you have the really mysterious ones, non-contact forces. Think about gravity or magnetism. They can pull or push on things from a distance, right through empty space. Kind of weird when you think about it.
Okay, and speaking of gravity, this brings up one of the single most common points of confusion in all of basic physics. We all do it. We use the words mass and weight like they mean the same thing, but in the world of science, they are totally fundamentally different. So let's clear this up right here, right now.
All right, here's the breakdown. Your mass, that's just the amount of stuff you're made of, all the atoms and molecules packed inside you. And that number, your mass, it never ever changes. It's the same on Earth, it's the same on the moon, it's the same if you're floating out in the middle of nowhere. But your weight? That's different. Your weight is the force of gravity pulling down on all that stuff. So, since the moon has way less gravity than Earth, you'd weigh a lot less there, even though the amount of you, your mass, is exactly the same. Makes sense, right? Okay, so we've got this idea of force down. But how does it actually work? What are the rules of the road? For that, we've got to turn to the official rulebook for motion, the one written by the man himself, Sir Isaac Newton.
So Newton, he came up with these 3 laws, and they're simple, but honestly, they are so profound. They describe pretty much everything about how forces and objects interact. And to make them a little easier to remember, we can give them some nicknames: the law of laziness, the law of acceleration, and the law of pairs.
All right, law number 1 is all about inertia, which I love to call the law of laziness. Seriously, objects are just lazy. They just want to keep doing whatever it is they're already doing. So if a soccer ball is just sitting on the grass, it's going to stay sitting there. If it's rolling along, it wants to keep rolling in a perfectly straight line at the same speed, basically forever, unless some other force comes along and messes things up, like friction from the grass or, your foot.
Okay, next up is the big one, the one everyone knows: F equals ma. This famous little equation is basically the recipe for how to change something's motion. It tells you that how fast something accelerates depends on just 2 things: how much force you use and how much mass the object has. So think about it. If you want to make something speed up faster, you've really only got 2 choices: push it harder or make it lighter. That's it. It's really that straightforward.
And that brings us to the third and final law, and this one's a big one. Forces never, ever act alone. They always come in pairs. So when you push on a wall, guess what? The wall is pushing back on you with the exact same force. When a rocket shoots hot gas down, that gas is pushing the rocket up. Every single push, every single pull in the entire universe is a two-way street. Okay, so in a perfect frictionless vacuum, those 3 laws are all you'd need. But, well, we don't live in a perfect vacuum. Here on Earth, there's this: complication. It's a force that's pretty much always there. Sometimes you're your best friend, and sometimes your worst enemy. Let's talk about friction, the ultimate frenemy. So what is friction? It's simply the force that fights against motion whenever 2 surfaces rub against each other. It's the reason a ball you roll across the floor eventually slows down and stops. It's why pushing a heavy box over a rough carpet is so much harder than pushing it on a slick, polished floor. The key thing is, it always pushes in the opposite direction of where you're trying to go. And this is why I call friction a frenemy. It really has this double life. On the one hand, it's absolutely essential. Without friction, you literally couldn't walk. Your feet would just slip,
Car brakes wouldn't work, you couldn't even pick up a glass of water. But on the other hand, it's a real pain. It causes machine parts to wear out, it creates a ton of useless heat, and it just generally slows everything down, wasting energy.
Okay, so let's take a quick second. We've got our building block, force, we've got Newton's 3 rules of the game, and we've got the ever-present complication of friction. So, what happens when we put it all together and actually do something? That's where our final big ideas come in: work, energy, and power.
Now, we all use the word work every day, right? But in physics, it has a very, very specific meaning. Here it is. Work is only done when you apply a force and that force actually makes an object move over a distance. So get this, if you push against the solid brick wall as hard as you can, you're going to feel exhausted. But if that wall doesn't move 1 single inch, then in the eyes of physics, you've done absolutely zero work. None.
So, if doing work is the actual action, then what gives you the ability to do it in the first place? Well, that would be energy. Think of energy as the currency of the universe. You have to spend it to get work done. And while it comes in a ton of different forms, we can think about 2 main types here. Kinetic energy, which is the energy something has because it's moving, and potential energy, which is basically stored up energy just waiting to be released.
Okay, just one last piece to this puzzle, and that's power. This is another one that gets mixed up a lot. Power isn't about how much work you do, it's about how fast you do it. So imagine this. You and a friend both have to lift the exact same heavy box onto a high shelf. You both did the exact same amount of work, right? But if you lift your box up in 2 seconds and it takes your friend 10 seconds, you are way more powerful. It's all about the rate.
All right, let's bring this all home with one simple example. You pushing a box across the floor. The actual push, that's the force. Because you made the box move, you've done work. The energy for all this came from the chemical energy stored in your muscles, which got converted into the box's energy of motion. And finally, your power is just a measure of how quickly you slid that box from point A to point B. See how it all just clicks together?
So there you have it, from a falling apple all the way to a planet in orbit. It really does all come down to a simple push or a pull, all governed by a handful of basic rules. But that leaves us with one last big idea to chew on. Think about Newton's third law. For every action, there's an equal and opposite reaction. If that's true, why does anything move at all? Why isn't the entire universe just stuck in a permanent cosmic tug-of-war? It's a great question. And the answer? Well, it's hidden in the details we've talked about today. Thanks for joining me for this.